Welcome to the first part of Lesson 6. In this lesson, we're going to learn about two new categories of reactions, the substitution and elimination reactions of alkyl halides. As we will see, in a substitution reaction, an atom or group of atoms is replaced with another atom or group, while in an elimination reaction, a base removes a proton, leading to the formation of a double bond. These reactions are fundamental to organic chemistry because they allow us to transform simple molecules into more complex structures, which is crucial in both laboratory synthesis and industrial applications. Throughout this lesson, we will explore the mechanisms, factors influencing these reactions, and the conditions under which each type of reaction is favored. Understanding these concepts will provide you with a solid foundation for more advanced topics in organic chemistry. Let's take a look at the outline for Lesson 6. This lesson is divided into two main parts. In the first part of the lesson, we will focus on nucleophilic substitution reactions. This part of the lesson begins with an overview of the reaction, and then covers the two main mechanisms by which this reaction can occur. Both SN2 and SN1 mechanisms will be discussed, and we will focus on highlighting their differences and the factors that influence each type. The effects of solvents and leaving groups will also be discussed, followed by practical examples to solidify understanding. In the second part of the lesson, we will move on to study elimination reactions. As before, Part 2 starts with a general overview, then examines the E2 and E1 reactions in detail. At the end of Part 2, we will discuss how to predict reactivity and the factors that determine whether a substitution or an elimination reaction is more likely to occur under given conditions. By the end of this lesson, a clear understanding of these fundamental reactions should be achieved, enabling application of this knowledge to more complex organic chemistry problems. Now, let's begin with Part 1. Let's start with a brief introduction to the concept of substitution and elimination reactions. Alkyl halides can undergo many different types of reactions, with substitution and elimination being two of the most important. In a substitution reaction, a nucleophile, which is an electron-rich species, replaces a group called the leaving group on the substrate. The substrate is the reactant molecule. The leaving group is an atom or group of atoms that can depart from the substrate with a pair of electrons. An elimination, on the other hand, is a reaction that involves a base that removes a proton from the substrate, which leads to the formation of a double bond. As a consequence, elimination and substitution can be competing reaction pathways on the same starting material. For example, when a halide reacts with a strong base, both types of reactions can occur. The elimination reaction typically produces an alkene as the major product, while the substitution reaction produces an alcohol as the minor product, along with other byproducts like water and a salt. Understanding the conditions that favor each pathway is crucial. This knowledge allows chemists to predict and control the outcomes of these reactions. This interplay between substitution and elimination will be explored further in this lesson. A good question to ask at this stage is, why do alkyl halides undergo these reactions? Let's go to the next page and try to answer this question by looking at the structure and properties of alkyl halides. Now, let's look at some possible reasons why alkyl halides are good substrates for both substitution and elimination reactions. First, the halogen atom attached to the carbon, in an alkyl halide, is electron withdrawing. This means that the halogen pulls electron density away from the carbon it's bonded to. As a result, the carbon becomes slightly electron deficient, giving it a partial positive charge. This partial positive charge makes the carbon an attractive target for nucleophiles, which are electron-rich species looking to donate electrons. This is why nucleophilic substitution reactions occur readily with alkyl halides. Additionally, this electron withdrawal also makes the carbon-hydrogen bonds adjacent to the halogen more acidic. This means that a base can easily remove a proton from these bonds, leading to the formation of a double bond. This process is the basis of elimination reactions. Secondly, halogens are good leaving groups. A good leaving group is an atom or group that can easily depart from the carbon atom, taking a pair of electrons with it. Halogens, like chlorine, bromine, and iodine, are stable after they leave because they can stabilize the negative charge. This stability is why they can leave the substrate readily during both substitution and elimination reactions. So, the combination of the electron withdrawing effect of the halogen and its ability to act as a good leaving group makes alkyl halides very reactive. This dual characteristic facilitates their involvement in both substitution and elimination reactions. Let's go to the next page and define a few helpful symbols and terms that can help us describe and understand these reactions. To better understand the reactivity of alkyl halides, it can be helpful to use specific labels for the positions on the molecule. One common method is to use Greek letters to denote different carbon positions relative to the halogen. The carbon directly attached to the halogen is called the alpha carbon. The next carbon in the chain is the beta carbon, followed by the gamma carbon, and so on. This labeling helps us specify where reactions occur on the molecule. For instance, substitution reactions typically happen at the alpha position, where the nucleophile replaces the leaving group. In elimination reactions, the base often removes a proton from the beta position, leading to the formation of a double bond between the alpha and beta carbons. Additionally, alkyl halides are classified based on the substitution of the carbon that bears the halogen. A primary alkyl halide has the halogen attached to a carbon that is connected to only one other carbon. A secondary alkyl halide has the halogen attached to a carbon that is connected to two other carbons. A tertiary alkyl halide has the halogen attached to a carbon connected to three other carbons. This classification is important because the amount of branching at the alpha carbon significantly affects the reaction mechanism. For example, primary alkyl halides typically undergo substitution reactions more easily, while tertiary alkyl halides are more prone to elimination reactions due to steric hindrance. Let's go to the next page and look at one other introductory issue related to the mechanism of substitution and elimination reactions. Specifically, how formal charges can change during the course of these reactions. Nucleophilic substitution reactions can involve different types of nucleophiles. In some cases, the nucleophile is negatively charged, while in other cases it is neutral. When the nucleophile is negatively charged, it donates a pair of electrons to the carbon atom, replacing the leaving group. This results in a neutral product and a negatively charged leaving group. For example, when a halide ion acts as the leaving group, the reaction produces a neutral organic molecule and a halide ion. On the other hand, when the nucleophile is neutral, it donates a pair of electrons to the carbon atom and becomes positively charged after the reaction. The leaving group is still negatively charged. For instance, if water acts as the nucleophile, the resulting product will have a positive charge on the oxygen atom, and the leaving group will be a halide ion. Despite these differences, the overall changes in both scenarios are similar. The nucleophile replaces the leaving group on the substrate, and arrows are used to keep track of electron movement and changes in charge. These arrows help us visualize how electrons are transferred during the reaction, which is crucial for understanding the reaction mechanism. Now that we've seen examples of substitution reactions, and how nucleophiles can be either negatively charged or neutral, let's look into the mechanisms that govern these reactions. Specifically, there are two main mechanisms to consider: the concerted mechanism and the stepwise mechanism. Let's explore these in more detail on the next slide. As mentioned on the previous slide, there are actually two possible mechanisms for nucleophilic substitution reactions. One is the so-called concerted mechanism, and the other is described as the stepwise mechanism. These two different mechanisms determine how the nucleophile and the leaving group interact with the substrate, and understanding them is key to predicting the outcomes of these reactions. Let's examine the concerted mechanism first. In a concerted reaction, all changes occur simultaneously in a single step. In the context of a concerted substitution reaction, this means that bond formation and bond breaking happen at the same time. The bond between the nucleophile and the substrate forms, while the bond to the leaving group breaks. This simultaneity also impacts the spatial orientation of where the new bond can form. Specifically, the new bond between the substrate and the nucleophile must form on the opposite side relative to the leaving group. This is known as the backside attack model, and it helps explain the stereochemical changes observed in these reactions. To understand why the nucleophile must approach from the back, imagine the nucleophile trying to reach the carbon atom where it will form a new bond. Since this new bond forms while the leaving group is still present, the nucleophile cannot approach the carbon atom from the same side as the leaving group. Instead, the nucleophile approaches from the opposite side, ensuring efficient bonding while the leaving group departs. This backside attack has a significant consequence for the product. The stereochemistry of the carbon atom is inverted. This inversion is a hallmark of the concerted substitution mechanism, leading to a distinct stereochemical outcome compared to other mechanisms. In contrast, the stepwise mechanism involves two distinct steps. First, the bond to the leaving group breaks, forming a positively charged carbocation intermediate. This step is slow because carbocations are not stable species. Once the carbocation intermediate is formed, it is then attacked by the nucleophile in a separate step. Because the intermediate carbocation is planar, because it is sp2 hybridized, the nucleophile can attack from either side, resulting in a mixture of stereoisomers. If a single chiral center is made in this process, the mixture is usually racemic. Understanding the distinction between these two types of mechanisms is crucial for predicting the outcomes of nucleophilic substitution reactions and determining which pathway is favored under different conditions. Let's start by looking at the concerted type substitution mechanism, which is called an SN2 reaction, on the next page. As mentioned, nucleophilic substitution reactions come in two varieties based on the mechanism involved in the transformation. These two mechanisms are called the SN2 mechanism, for the concerted pathway, and the SN1 mechanism for the stepwise pathway. Let's look at the SN2 mechanism first. SN2 stands for bimolecular nucleophilic substitution. The letter S in this label stands for substitution, indicating that one group is being replaced by another. The letter N stands for nucleophilic, meaning the substitution is driven by a nucleophile, an electron-rich species that donates a pair of electrons to form a new bond. The number 2 denotes bimolecular, indicating that the rate-determining step of the reaction involves two molecules, the nucleophile and the substrate. Now, let's discuss some key observations regarding the SN2 reaction. First, let's talk about the inversion of stereochemistry. In an SN2 reaction, the nucleophile attacks the carbon atom from the side opposite the leaving group. This is because the leaving group, which is still attached to the carbon, blocks the nucleophile from attacking from the front. This backside attack causes the configuration around the carbon to invert, much like an umbrella turning inside out in the wind. For example, consider the reaction of hydroxide ion with 2-bromobutane. The hydroxide ion approaches from the back, where the bromine atom is leaving, leading to the formation of 2-butanol with an inverted configuration. If the starting material has the R configuration, the product will have the S configuration, illustrating this inversion. Now let's discuss the rate of SN2 reactions. Because the reaction mechanism is bimolecular, meaning that it involves two molecules, the rate of an SN2 reaction depends on the concentrations of both of those molecules, specifically the substrate and the nucleophile. This is because the reaction involves a single transition state, where both the nucleophile and the substrate are colliding with each other. We can express this by writing the rate equation for the reaction. The rate law for an SN2 reaction is given by the equation. Reaction rate is equal to the rate constant multiplied by the concentration of the substrate times the concentration of the nucleophile. This means that if you double the concentration of either the substrate or the nucleophile, the reaction rate will also double. This dependence on both reactants is a defining characteristic of SN2 reactions. A third observation for SN2 reactions is that the structure of the substrate has a massive impact on the rate of the reaction. So much so that some substrates do not react at all in these reactions. Let's take a look at this effect on the next page. In SN2 reactions, the rate is significantly influenced by the substitution at the alpha carbon. Consider the illustration below, which summarizes this effect. When the alpha carbon is tertiary, meaning it is attached to 3 other alkyl groups, the steric hindrance is very high, making it difficult for the nucleophile to attack the carbon bearing the leaving group. As a result, the reaction rate is very low. For secondary carbons, the steric hindrance is less severe, allowing the nucleophile to approach more easily. This leads to a moderate reaction rate. Primary carbons exhibit even less steric hindrance, making it easier for the nucleophile to access the alpha carbon, resulting in a much higher reaction rate. Methyl groups have the least steric hindrance, allowing the nucleophile to attack the alpha carbon very easily, which results in the highest reaction rate among these examples. Let's summarize what we know so far about SN2 reactions. We have seen 3 important observations of these reactions. 1. Inversion of configuration. During the SN2 reaction, the nucleophile attacks the carbon from the opposite side of the leaving group, leading to an inversion of configuration at the alpha carbon. 2. Bimolecular rate. The rate of the SN2 reaction depends on the concentration of both the substrate and the nucleophile, making it a bimolecular reaction. This means that both the substrate and the nucleophile have an impact on the rate. This is underscored in point 3. 3. Impact of substrate structure. The structure of the substrate significantly affects the reaction rate. Primary substrates react faster than secondary substrates, and tertiary substrates are the least reactive due to increased steric hindrance. These key points highlight the critical factors that influence SN2 reactions and help in understanding their behavior in different chemical contexts. Let's move on to the stepwise substitution mechanism, which is called the SN1 reaction. The second mechanism type observed in nucleophilic substitutions is the SN1 reaction. The term SN1 stands for substitution, nucleophilic, and unimolecular. It is called SN1 because the rate-determining step of the reaction involves only one molecule. This, among other features, distinguishes it from the SN2 type reactions. As mentioned, the SN1 mechanism proceeds through a stepwise process. The first step is the formation of a carbocation intermediate. This occurs when the leaving group departs from the substrate. This step is slow and therefore determines the overall rate of the reaction. Hence it is called the rate-determining step. The rate-determining step is crucial because it is the slowest step in a reaction pathway and limits the overall reaction rate. The formation of the carbocation intermediate has a dramatic influence on the outcome of the reaction, making it very different from SN2 reactions. The carbocation intermediate that is formed is planar, meaning it has a flat, triangular shape. This causes a distinct change in the stereochemical outcome for the reaction. Specifically, products of SN1 reactions exhibit racemization of stereochemistry. This occurs because the planar carbocation intermediate can be attacked by the nucleophile from either side. As a result, the reaction produces a mixture of products with both inversion and retention of configuration. Essentially, this leads to a racemic mixture containing equal amounts of both enantiomers. Unlike SN2 reactions, where the nucleophile specifically attacks from the opposite side of the leaving group, resulting in only the inversion product, SN1 reactions allow the nucleophile to approach from either face of the planar carbocation, resulting in two different configurations. As mentioned, SN1 reactions are described as having unimolecular kinetics. A unimolecular reaction is a type of chemical reaction in which the rate-determining step involves only a single molecule. This means that the reaction rate is dependent solely on the concentration of this one reactant. For SN1 reactions, the rate depends solely on the concentration of the substrate. The concentration of the nucleophile does not affect the rate of the reaction. This is because the rate-determining step is the formation of the carbocation intermediate, which only involves the substrate. The nucleophile has no role in this step. Now that we have a basic understanding of the two types of nucleophilic substitution reactions, let's go into a little more detail on other factors that have an impact on the reaction. Specifically, we need to discuss both the leaving group and the solvent used for the reaction. We'll start with leaving groups on the next page, as those will have the most dramatic effect on the reaction. The leaving group is a critical component of the substrate in a nucleophilic substitution reaction, and some atoms or groups of atoms make much better leaving groups than others. Let's think about what a leaving group actually does in a substitution reaction. Fundamentally, a leaving group must be able to stabilize the negative charge it acquires after departure, allowing the reaction to proceed smoothly. So a good leaving group is essential, because it reduces the energy barrier for the reaction, making the process more efficient. The best leaving groups are stable anions. In other words, a leaving group is more effective if it is stable once it has left the substrate molecule. As we will see in this discussion, good leaving groups are very often the conjugate bases of strong acids. For example, consider iodide. When iodide is the leaving group, the relative rate of reaction is very high, around 30,000. This high reactivity is due to iodide being a very stable anion once it leaves, thanks to its large size and low charge density. Hydroiodic acid, from which iodide is derived, has a very low pKa of approximately -10, indicating that it is a strong acid. This means that iodide, as its conjugate base, is very stable. Next, we have bromide. When bromide is the leaving group, the relative rate of reaction is about 10,000. Bromide is also an excellent leaving group. Hydrobromic acid has a pKa of around -9, making it a strong acid, and bromide a stable anion. Chloride comes next. When chloride is the leaving group, the relative rate of reaction drops to about 200. While still considered a decent leaving group, chloride is less effective than bromide and iodide. Hydrochloric acid has a pKa of approximately -7, indicating it is a strong acid, though weaker than hydroiodic and hydrobromic acids. This is because chloride is less stable as an anion than bromide and iodide. Chloride has a much smaller radius, and this means it has higher charge density, making it a less stable anion than bromide or iodide, and thus a worse leaving group. Finally, we have fluoride. When fluoride is the leaving group, the relative rate of reaction is only 1. Fluoride is a poor leaving group. This is because it is a small ion with high charge density, making it much less stable when it leaves. Hydrofluoric acid, from which fluoride is derived, has a pKa of around 3.2, indicating that it is a much weaker acid compared to the others. Therefore, fluoride, as its conjugate base, is not very stable. To summarize the trend in leaving group reactivity, iodide is the best, followed by bromide, then chloride, and finally fluoride. This trend correlates with the relative rates of reaction and the stability of the anions. Iodide, being the most stable, is the most reactive, whereas fluoride, being the least stable, is the least reactive. Notice that there are several groups listed that are even worse leaving groups than fluoride. These groups include hydroxide, amide anion, and alkoxide anions. These groups are all examples of bad leaving groups. This is because they are highly unstable once they leave the substrate, and we can use pKa values to help us rationalize and predict this fact. Here's how it works. These anions are derived from acids that have relatively high pKa values. In fact, their conjugate acids all have pKa's above 10. For example, hydroxide's conjugate acid is water, which has a pKa of about 15.7. This means that water is a very weak acid, and that hydroxide is not a very stable anion. The conjugate acid of amide anions are amines, which have a pKa of 35, and alkoxide's conjugate acids are alcohols, with a pKa around 15. A good rule of thumb is if the pKa value for an acid is above 10, that means its anion is a strong enough base to make it a poor leaving group. To summarize, understanding the role of pKa values can help us predict leaving group ability. The lower the pKa of the conjugate acid, the stronger the acid, and the more stable the conjugate base. Let's turn our attention to another important consideration for nucleophilic substitution reactions: the reaction solvent. When planning a reaction, the choice of solvent can have a profound impact on the rate of the reaction. In this part of the lesson, we will look at the different types of solvents, their classification, and which solvents are best for SN1 and SN2 reactions. First, we need to discuss solvent polarity. We can generally classify a solvent as being polar or nonpolar, based on its structure and the atoms and functional groups present. Nonpolar solvents are comprised of molecules that have no significant charge separation, resulting in a lack of dipole moment. These solvents dissolve nonpolar substances well, but are ineffective at dissolving polar or ionic compounds. Examples of nonpolar solvents include hexane, benzene, and toluene. Polar solvents, on the other hand, are comprised of molecules that have significant partial positive and partial negative charge separation on their structures, due to differences in electronegativity between their atoms. These differences in electronegativity create a dipole moment, allowing polar solvents to dissolve ionic and other polar substances effectively. Water, acetone, and ethanol are examples of polar solvents. Polar solvents can be further divided into two categories: polar protic solvents and polar aprotic solvents. Polar protic solvents are characterized by their ability to donate a hydrogen bond, due to the presence of a hydrogen atom bonded to a strongly electronegative atom, such as nitrogen or oxygen. This creates a strongly electropositive hydrogen atom, making the compound an effective hydrogen bond donor. In contrast, if a molecule does not have a hydrogen atom bonded to an oxygen or nitrogen, it is classified as a polar aprotic solvent. Several examples of solvents in both categories are shown in the tables below. Notice that in all polar protic solvents, a hydrogen atom, labeled in red, is directly bonded to oxygen or nitrogen. In all polar aprotic solvents, this feature is absent. Now that we can distinguish between polar protic solvents and polar aprotic solvents, we need to determine which type of solvent is the best to use in a substitution reaction. Let's look at how this choice is made on the next page. Let's discuss the effects of solvents on nucleophilic substitution reactions, and understand why different types of solvents are best for SN1 and SN2 reactions. The first consideration in solvent selection for these reactions is whether to use a polar or nonpolar solvent. Note that in substitution reactions, we are going to be using an ionic compound, such as sodium chloride or sodium bromide, as the source of our nucleophile. So our reaction solvent will need to be able to dissolve these salts in order for there to be enough nucleophile to participate in the reaction. This is one of the main reasons why polar solvents are used, rather than nonpolar solvents, in nucleophilic substitution reactions. Polar solvents are generally preferred over nonpolar solvents for substitution reactions because they can dissolve ionic nucleophiles and stabilize the ionic intermediates, or transition states that occur during these reactions. Nonpolar solvents, on the other hand, lack the ability to effectively dissolve ionic species, which is essential for the reaction to proceed efficiently. The second consideration is whether to use polar protic or polar aprotic solvents. For SN2 reactions, polar aprotic solvents are the best choice. Polar aprotic solvents, such as acetone, dimethyl sulfoxide, abbreviated DMSO, and acetonitrile, cannot form hydrogen bonds with the nucleophile. As a result, these solvents do not solvate the nucleophile effectively, keeping it highly reactive. In other words, by not forming hydrogen bonds with the nucleophile, these solvents ensure that the nucleophile remains free and ready to attack the substrate efficiently. This increased reactivity of the nucleophile lowers the activation energy required for the substitution, and increases the rate of the SN2 reaction. In contrast, SN1 reactions benefit from polar protic solvents, such as water, methanol, and ethanol. These solvents do form hydrogen bonds, because they have hydrogen atoms bonded to strongly electronegative atoms. During the SN1 reaction, the rate-determining step is loss of a leaving group with a negative charge. Polar protic solvents facilitate this step by donating hydrogen bonds to the leaving group, lowering its charge density, and thus stabilizing the transition state. This stabilization lowers the activation energy, making the reaction proceed faster. To summarize, for SN2 reactions, polar aprotic solvents are best because they keep the nucleophile reactive by not forming hydrogen bonds, thus lowering the activation energy and speeding up the reaction. For SN1 reactions, polar protic solvents are ideal because they stabilize the carbocation intermediate and the leaving group through hydrogen bonding, lowering the activation energy and facilitating the reaction. Now that we have a better understanding for the requirements of SN1 and SN2 reactions, it's time for us to see some examples. On the next several slides, we will go over many examples of each reaction type, so we can get more familiar recognizing these transformations. When we finish the example reactions, we will conclude this part of the lesson by practicing drawing a few example mechanisms. Let's go to the next page and get started. Let's start with some examples of SN1 reactions. In the table below, I have included several examples that incorporate differences in substrate structure, nucleophile, and stereochemistry. Let's go through each of the examples together, focusing on identifying the substitution that is taking place, and accurately drawing the product. In the first example, a cyclohexane derivative with an iodide group reacts with sodium chloride. Here, the iodide group is replaced by a chloride ion. To draw the product, replace the iodine atom on the cyclohexane ring with a chlorine atom. The nucleophile was the chloride, the leaving group was the iodide, and the substrate was transformed into the indicated product. In the second example, a bromo-substituted heptane reacts with sodium hydrosulfide. The bromide group is replaced by a thiol group. Notice that the substitution is taking place at a chiral carbon. Recall that the mechanism for SN1 reaction involves the loss of the leaving group to generate a trigonal planar carbocation. Due to the planar nature of the carbocation, the nucleophile, which is the sulfur atom in SH, can attack from both the front or the back, leading to a racemic chiral center. To draw the product, replace the bromine atom with an SH group at the same position, but make sure to show both possible enantiomers, as a racemic mixture will be formed. In the third example, a cyclohexane derivative with a hydroxyl group reacts with hydrobromic acid. In this case, the hydroxyl group, which is a bad leaving group, is protonated by acidic hydrobromic acid. This extra hydrogen on the hydroxyl group gives the oxygen a positive formal charge. The leaving group is now a water molecule, not hydroxyl. After leaving as a water molecule, the hydroxyl is replaced by a bromide ion. To draw the product, replace the OH group on the cyclohexane ring with a bromine atom. In the fourth example, a cyclohexane derivative with a bromide group reacts with sodium cyanide. Cyanide is a nucleophile with the structure of C triple bond N and a negative formal charge at carbon, which has a non-bonding electron pair. Cyanide is nucleophilic at this negatively charged carbon, and that is where we will connect the cyanide to our substrate. To draw the product, replace the bromine atom with a CN group, drawing the bond between the carbon atom of the substrate and the carbon of the cyanide group. In the fifth example, an iodo-substituted cyclopentane, with a chiral center at the carbon that bears the leaving group, reacts with sodium bromide. The iodide group is replaced by a bromide ion. Because this is an SN1 mechanism, the product is formed as a racemic mixture. To draw the product, replace the iodine atom with a bromine atom at the same position, showing both possible enantiomers. In the sixth and final example, a chloro-substituted pentane reacts with sodium acetate. Acetate is the conjugate base of acetic acid, and is nucleophilic at the negatively charged oxygen. So in this reaction, the chloride group is replaced by an acetate group. To draw the product, replace the chlorine atom with an acetate group, drawing the covalent bond between the tertiary carbon atom and the oxygen that acted as the nucleophile. These examples illustrate the various transformations in SN1 reactions, highlighting the substitution of leaving groups by nucleophiles and the potential for stereochemical outcomes, such as racemic mixtures, due to the planar nature of the intermediates. Let's go to the next page and look at several examples of SN2 reactions. Let's go through each of the following SN2 reaction examples in detail, focusing on the transformations that take place and explaining how we draw the product. In the first example, an alkyl bromide substrate is treated with sodium hydroxide. Here, the bromide group, which is the leaving group, is replaced with a hydroxyl group, which is the nucleophile. To draw the product, simply replace the bromine atom on the alkyl chain with a hydroxyl group, resulting in an alcohol. In the second example, the substrate R2-bromobutane reacts with sodium hydrosulfide. The bromide group is substituted with a thiol group. This reaction proceeds with inversion of configuration. To draw the product, replace the bromine atom with an SH group, giving the product shown, being careful to note the change in stereochemistry. In the third example, a cycloalkyl bromide substrate is treated with sodium cyanide, the nucleophile. The bromide group is substituted with a cyanide ion, being sure to draw the bond from the carbon on the cyanide group. This reaction also proceeds with inversion of configuration. To draw the product, replace the bromine atom with a CN group, resulting in a nitrile, noting the change in stereochemistry. In the fourth example, a 2-bromopentane substrate, with a chiral center at the location of the leaving group, reacts with sodium acetate, the nucleophile. The bromide group is substituted with an acetate group. This reaction also results in inversion of configuration. To draw the product, replace the bromine atom with an acetate group, resulting in an ester, showing the inversion of stereochemistry. In the fifth example, a benzyl bromide reacts with a thiolate. Note that the thiolate nucleophile has a chiral center, but that this chiral center is not involved in the substitution reaction, and therefore its configuration will remain unchanged. The bromide is substituted with the thiolate group, with the new bond forming between the sulfur and the carbon atom, resulting in a sulfide. To draw the product, replace the bromine atom with the thiolate group. In the sixth example, a benzyl oxyanion nucleophile reacts with methyl iodide, which is the substrate. Notice that this reaction was written differently than the previous examples. So far we have always written the substrate before the reaction arrow, and the nucleophile as a reagent above the arrow. The reaction is still the SN2 pathway. To draw the product, we simply need to connect the oxygen atom to the carbon atom of the methyl group, noting that the iodide departed during the substitution. These examples illustrate the various transformations in SN2 reactions, highlighting the substitution of leaving groups by nucleophiles and the stereochemical outcomes, such as inversion of configuration, due to the backside attack mechanism. Let's go to the next page and look at a few example mechanisms before we wrap up this part of the lesson. Consider the substitution reaction shown here. Let's suppose we wanted to explain how this transformation occurs by drawing a step-by-step mechanism. The first thing we should do, after establishing that it is a substitution reaction, is to identify the type of substitution mechanism, either SN1 or SN2, that is likely occurring. To do this, we consider several key factors. First, the substrate is a tertiary alkyl chloride. We know that tertiary alkyl halides react very slowly in SN2 reactions, but are excellent substrates for SN1 reactions. They are slow in SN2 reactions due to steric crowding around the leaving group, and they work well in SN1 reactions because a carbocation at that location would be stabilized by 3 alkyl groups, making it somewhat stable. Additionally, the solvent is water, a polar protic solvent that stabilizes both the carbocation intermediate and the leaving group, favoring the SN1 mechanism. Now that we have established the likely mechanism, we can go ahead and get started drawing out all of the steps. Recall that the SN1 mechanism proceeds through a 2-step process. In the first step, we have a loss of leaving group, which in this case is the chloride ion, which leaves the substrate, which is shown by the electron flow arrow, pointing from the bond between the carbon and chlorine to the chlorine atom. This departure leaves behind a positively charged carbon, forming a carbocation. In the second step of an SN1 reaction, we have a nucleophilic attack occur. In this example, a water molecule acts as a nucleophile and attacks the carbocation. The electron flow arrow points from the lone pair of electrons on the oxygen atom in the water molecule to the positively charged carbon. This attack forms an oxonium ion, where the oxygen is now bonded to the carbon and carries a positive charge due to the extra hydrogen atom. This oxonium is not the final product, so we need one additional step. For the final step, we have a proton transfer. The electron flow arrow shows the transfer of electrons from one of the hydrogen-oxygen bonds to the oxygen atom, leading to the loss of a proton. This results in the formation of the alcohol product, and the proton associates with the chloride ion to form hydrochloric acid. This example illustrates the characteristic steps of an SN1 mechanism: the loss of the leaving group, the nucleophilic attack, and the proton transfer, with clear indications of electron flow that guide each step of the process. Let's consider another example reaction, as shown below. Pause the video and see if you can identify the type of reaction mechanism that is occurring, and try to draw it out step by step. This mechanism is a bit different than the one we looked at on the previous page, so it will require a slightly different series of steps, but I think you can probably come up with something reasonable. When you unpause the video, we will review the mechanism together. Welcome back. As before, our first task is to identify the type of reaction that is occurring. We can see that there is a substitution taking place, as the hydroxyl group is replaced with a bromide. Given that this is a substitution, we need to determine which type of substitution is likely. Based on the information presented, this reaction is an SN1 type reaction. We can identify this reaction as an SN1 mechanism, based on several key factors. First, the substrate is a tertiary alcohol, which is prone to SN1 reactions, because the resulting carbocation can be stabilized by 3 alkyl groups. This stabilization makes the formation of the carbocation intermediate more favorable. Additionally, the solvent is hydrobromic acid, which has significant protic character, due to the electronegativity of bromine, that stabilizes both the carbocation intermediate and the leaving group, favoring the SN1 mechanism. The only issue is that hydroxide cannot act as the leaving group. The reason for this is that hydroxide is a strong base. The pKa of hydroxide's conjugate acid, which is water, is 15.7. Remember that anything above 10 is representative of a bad leaving group. So if it isn't hydroxide, what is the leaving group? That's right, water. Under acidic conditions, we can protonate the hydroxide group, generating an oxonium ion. This ion can leave as water, which is a great leaving group. Water's conjugate acid, hydronium, has a pKa of approximately -1.7, showing us that it is an excellent leaving group. Let's put all of this into a reaction mechanism. The reaction mechanism involves 3 main steps: proton transfer, loss of the leaving group, and nucleophilic attack. Let's go through each step. First, the hydroxyl group of the tertiary alcohol undergoes proton transfer with hydrobromic acid. This protonation is shown by the electron flow arrow from the hydroxyl group to the hydrogen atom of HBr, resulting in the formation of water as a good leaving group and generating a bromide ion. Next, the water molecule leaves the substrate. This step is depicted by the electron flow arrow pointing from the bond between the carbon and the now protonated hydroxyl group to the oxygen atom. The departure of the water molecule leaves behind a carbocation. In the final step, the nucleophilic attack occurs. The bromide ion, generated in the first step, attacks the carbocation. This is shown by the electron flow arrow pointing from the lone pair of electrons on the bromide ion to the positively charged carbon. This nucleophilic attack results in the formation of the final product, where the bromide ion has replaced the hydroxyl group, and water is released as a byproduct. In summary, this example illustrates the characteristic steps of an SN1 mechanism. Proton transfer to make the hydroxyl group a good leaving group, loss of the leaving group to form a carbocation, and nucleophilic attack by the bromide ion. These steps, with clear indications of electron flow, guide each part of the process. And that concludes the first part of Lesson 6. In the next part of the lesson, we will continue learning about the chemistry of alkyl halides, this time by focusing our attention on elimination reactions. We will learn about the 2 different mechanisms that are possible, and practice drawing the products of these reactions, along with their mechanisms. We will also learn how to identify which pathway, substitution or elimination, is more likely to occur under a given set of conditions. Thank you for watching. See you in the next video.